All right, so these functional groups, this is what we have over here, all these guys. And we'll just zoom in on them one at a time. All right, so the first one of these functional groups is called an aldehyde. So what you need for an aldehyde is you need a carbonyl group, and a carbonyl group is this. There are several different functional groups that have this carbonyl group, this carbon doubly bonded to an oxygen, and that provides functionality, a way to distribute electrons within that covalent bond that change how it chemically reacts. So we've got this carbonyl group, and for it to be an aldehyde, it has to have a hydrogen on at least one side. So that makes the aldehyde specific to its location on an organic molecule. So what do you know about the aldehyde? Where does it have to be located on the molecule? Has to be terminal. Since one side has to be a hydrogen, then if it's on a chain, it's got to be at the end. So if you're looking in the middle of a molecule for an aldehyde, it can't be there. It's got to be on the end. You can have an aldehyde that just has hydrogens, but then it can't be part of a chain. And so that's the most simplistic one. The common name for that guy is going to be formaldehyde. I'm sure we've heard that word before. And it's a antimicrobial, and that's what we use to like sterilize something that we want to keep. So did you guys take biology? Did you mess with the cats? So we've got cats for anatomy and physiology, and for the biology class, we've got, you can look at the cats, they've got like hearts and lungs and eyeballs of different animals, and it's all soaked in formaldehyde along with some other stuff. And things can't grow within the formaldehyde itself. Sorry for Steve. So I'm looking for a particular picture. I'm just gonna have to open up the 7 notes. So here's the molecule ribose in its straight chain form, not in its cyclic form. And you can see that there's a carbonyl group here and an H. So that makes this an aldehyde. It's at the end. And this is the ribosin RNA. It's the R for RNA. There's glucose. So glucose is another aldehyde sugar. So the aldehyde thing, functional group is phenomenally important. I mean, it doesn't get much more important than glucose for mammals. So there you go. It's on one of the most important molecules. The next one is called an ether. Have you heard that term before? Where and under what circumstances have you heard ether used? What was the last thing you said? It's ether. Yeah, so you need to have an oxygen that's sandwiched between two carbons. It could just be that. It could be like a carbon on each side of it with some hydrogens, and that's the smallest version. So unlike the aldehyde, which has to be terminal, this can't be terminal, right? There has to be a carbon on both sides. So you won't find this thing at the end of a molecule. So non-terminal structure. I think the most common use of ether traditionally has been as an anesthetic. So it's a respiratory irritant, but it also knocks you out. So if you were to breathe ether, you will pass out. And this is what they use for surgeries for a long time. They would just put a little rag stuffed with or soaked with ether, and you'd breathe it in and you'd pass out, and they would cut your leg off and sew it back up, and hopefully you didn't wake up during the sawing process. So this is a very common thing for Civil War. If you ever saw the Dances with Wolves movie, they were about ready to do that to the main character before he decided to stir things up. Okay, next one, kind of hard to read, but it's an ester. So what I have with an ester is I've got an oxygen that's sandwiched between two carbons, but one of those carbons has to be one of these carbonyl carbons. So the chemistry completely changes when one of the carbons that the oxygen is attached to is a carbonyl. The esters are pretty simple. Have you heard of ester before? No, there's a name. Usually quite fragrant, fairly volatile, and provide a lot of flavor. They also cause things to ripen. So once a piece of fruit starts emanating its esters, it will itself ripen more quickly, and anything it gets next to will ripen more quickly. You've probably heard the term or the phrase, one bad apple. One bad apple can ruin the bunch or the bushel. So what that means is if you've got one apple that has ripened and it's to the point where it is ripe and it is sending off those esters, it will cause all the rest of the apples in the bushel to ripen fast. And so by the time it gets to where it's supposed to go, a bunch of them will have gone bad because this one apple is sending out the esters and the other apples are basically absorbing that and realizing, oh, it's my time to start to ripen. So you need to make sure that all the fruit, regardless if it's an apple or something else, needs to they need to be at the same ripeness level. Otherwise, you can get them to ripen before or after you want them to. And going along with that, if you've got some fruit and it's not ripe, and let's say you need it ripened in a day or so, you can put a ripe fruit in a bag with it. So you buy some bananas and they're green, but you need them, tomorrow morning. So you can take a ripe apple or pear or pineapple or another banana, and you can
put them in a bag together and you'll get them to ripen much more quickly. So these are just all different ester molecules. Okay, this is an alkyne. It's ALKYNE, and this is carbons that are triply bonded to each other. The most common one is probably acetylene, and that's used for welding. What did we say about multiple bonds between carbons, about reactivity? Goes up because those electrons are on the outside. They're not in between the two carbons. They're above and below or in front and back. So this has electrons above and below the bond and on either side of the bond. So those 4 electrons in those 2 extra bonds, in the double bond and the triple bond, which is really just 2 double bonds, forming those 3 connections between those carbons, is phenomenally reactive, which is why you can get the acetylene to melt metal fairly easily. The next one is a carboxylic acid. What you need is an OH attached to a carbon, but it has to be a carbonyl carbon. And so that was the acetic acid that you guys used in the lab a couple of times. Any organic acids. This is why vitamin C is sour. Ascorbic acid, citric acid. This is why lemons and limes and oranges have that tartness to them because of that carboxylic acid. Can you tell me something about the carboxylic acid's position on the molecule? It's got to be terminal because it ends with an H. It ends with an OH. So anything that ends in an H has got to be at the end. So carboxylic acids are going to be on the end. So next one down here is an alkene, ALKENE, as opposed to the ALKYNE. So YNE is 3 bonds, ENE is 2 bonds. The triple bond one, we pronounce the Y as if it was an I with a hard E. So it's ine, so alkyne, and then the ENE is alkene. So again, an E followed by a silent E. So I've got alkynes and alkenes. So the alkenes is just a single double bond going along with the single bond. So it's very reactive, but it's less reactive than triple bond. And so you have to have 2 carbons connected to each other, doubled up. Then we've got an alcohol, which kind of looks like a carboxylic acid, except that the OH is attached to a carbon that's not a carbonyl. That's the main difference. Also has to be terminal because there's an H after the O, so I can't make it go any further. If I look at this glucose molecule here, there are OHs all over it. Pretty much every carbon has a hydroxyl group on it. Same thing with fructose. OH is OH, 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 another OH. So those OH groups are very important to the molecule's structure. An amine is going to be a nitrogen that's connected to a carbon. It could be connected to 1 carbon, 2 carbons, or 3 carbons. The important thing to realize is none of those carbons can be carbonyl carbons. So this is, where have you heard that amine before? Amino acids.
What are the carbonyls?
A carbon doubly bonded to an oxygen. So this is a carbonyl right here. And this is a carbonyl right here. The carbonyl itself isn't a functional group. It makes it, the functional group is created based off of the position of a carbonyl group. It's going to be here. Yeah. So here are a bunch of amino acids. And what do you notice about this amino acid, about these amino acids?
That's carboxylic acid, right?
So it's amino acid, so there has to be an acid. So there's your carboxylic acid. A C doubly bonded to an O, and that C has an OH attached to it. So that right-hand side is a carboxylic acid. And then what else we got?
It's the one we're just at,
Which was what?
amine.
Amine, yeah. And this is an amino acid, right? So it's letting you know that one side is an amine and that the other side is the acid. Do you remember what we talked about with nitrogens within molecules? They perform what function? They're bases because they've got a lone pair of electrons on them. They're all Lewis bases. So this amino acid is actually a base on one side and an acid on another side. That way they can facilitate a reaction even amongst themselves. So it could react with itself, or it could react with these things right next to each other. So if this is an acid and this is a base, then these two things would react with each other. And so that's what we're trying to do when we're making proteins, is get these chains to hook up with each other. So I like to think about them being like different kinds of Legos. They snap together very easily because one side wants to snap into the other side. The next one is an amide. And the AM is letting you know that there's another nitrogen there. But this amide is a little different than the amine because the attached to a carbonyl. And the amide and the amine have different properties. This next one is called a phenyl or a benzyl. And it's a benzene ring that we talked about before with the delocalization of the electrons. So it's a 6-carbon ring where you have those rotating double bonds. So not true double bonds, but the bonds, those electrons, those 6 valence electrons that are allowed to shift their position on the top and the bottom, forming like a double donut structure over the flat molecule. So you can attach phenols within molecules. Here's an example of several of these things. So here's aspirin, acetylsalicylic acid. What functional groups that we've talked about so far do you see on this molecule? So there's a carboxylic acid at the top, a C double bond O, OH. What else we got? sorry, what'd you call it?
Aldehyde.
An aldehyde, yep. I've got an oxygen sandwiched between two carbons, but one of those carbons is a carbonyl carbon. So that left-hand side, that's an aldehyde. And then, sorry, did you say aldehyde? No, not aldehyde. It's not terminal. If it was an aldehyde, that CH3 at the end would just be an H. But since it's not an H, that there's a carbon on both. It's an ether. No, ether, ester. It's an ester, not an ether. If it was an ether, then there wouldn't be a carbonyl group. But it's there's a carbonyl group there. C double bond O, O, and then another carbon. So that thing is an ester. It looks like an ether, but one of the C's has a double bond O on it, so it's an ester. And then what's the last piece? This is basically just three functional groups stuck together. Carboxylic acid and ester, and then what's the third functional group? The phenyl. Yeah. So I got a benzene ring, and one of the things attached to the benzene ring is the carboxylic acid. The other thing that's attached to it is an ester. Okay. This next one is called an alkyl halide. And so this is one of the halogens, fluorine, attached directly to, it has to be terminal because the hydroxyl, sorry, the halogens can only make one bond. So they're always going to be on the outside, on the edge or the side of it. The next one is a ketone. And the ketone is kind of like the aldehyde, except it can't be at the end. It has to have, the carbonyl group has to have a carbon on both sides. So the smallest ketone possible has 3 carbons in it. Last thing on this list, this diagram is a heterocyclic ring. So what's that prefix hetero mean? Different. So this is, how is this a heterocyclic ring? About that it's a ring structure and the components of the ring aren't all the same atom. So it starts off with a nitrogen, then it goes to a carbon and another carbon and then a nitrogen and then another carbon. And so that's why it's a heterocyclic ring structure as opposed to the phenyl, which is a homocyclic ring structure, all carbons. Do we know what this is? It's a nucleotide. Do we know what that word means? What that's used in?
I should.
It's the N in DNA. And so what I have here is a phosphate group, sugar, and a nitrogen base. So heterocyclic ring structures, so a pair of them. And then another heterocyclic ring structure. This is deoxyribose. And the reason it's deoxyribose instead of just ribose is there isn't an OH group here. So the deoxy means missing an oxygen. If this was ribose, there'd be a hydroxyl group there pointing up. But since, and that's the, this thing would be the same if the OH was here, except we call this RNA because it would be ribose nucleic acid. And so then that would be found in RNA if the OH group was there. But this doesn't have the OH group, so that means deoxyribonucleic acid. So then that makes this one of the stair step
one of the halves of a stair for your DNA. The phosphates are the things that attach to each other in the long chain. And the nitrogen-based nucleotides reach across to the other chain or hydrogen bonds, so those guys connect up. So what I've got here is a couple of heterocyclic ring structures, 3 of them, and a D. These are actually all amines as well. And there's an alcohol group. And what would this thing here be? That's detail. It's an ether. It's a carbon connecting, or an oxygen with an oxygen with a carbon on each side, but neither one of those carbons are a carbonyl carbon. So that ether structure is in that sugar. It's also in, here's fructose. So the fructose structure in cyclic form would form a ketone, but then when I move over to a cyclic form, it's carbon, oxygen, carbon, so it forms a ketone. And then if I slide up, here's my glucose molecule. See another ether. Also, 5 different alcohol groups attached to it. Those are all alcohols because they are OH groups attached to a carbon, and that carbon is not a carbonyl carbon. So that makes them all alcohols. So when somebody says alcohol sugar, like, okay, all sugars are alcohol sugars. That's redundant, but it's because those sugars all have alcohol groups attached to those carbons. The only one that doesn't have an alcohol group on it is this guy right here. And that's because its alcohol group was this oxygen. And that H went away and then it formed this ring structure. So you can see if I come up here, so I've got a carbonyl group and then all of these OH groups on here. And what ends up happening is this carbon right here attaches to that oxygen right there. And then that's how you get your ring structure. It goes from that straight lace structure to this 6-membered ring. Okay. So we'll talk about all of these things. I'm not expecting you to be able to, I will expect you to be able to point to something and say, that's an ether, or that's a heterocyclic ring structure. I'm not going to expect you to be able to name them, name their structures, just point out that that functional group is there. Make sure that is what we're doing. Yeah, okay. Okay. So again, these functional groups are what make organic molecules interesting. If I don't put the functional groups on, then I have fuel. I've got gasoline, I've got diesel, I've got lubricants, I've got natural gas. But when I start attaching these things on, then interesting things occur. So we're going to start off with the alkanes, which we didn't talk about at all. But the alkane is carbons and hydrogens and nothing, no double or triple bonds attached to them. So it's the most simplistic form. We've seen, you guys put one up on the homework today, that propane. And you know it's an alkane because it was propane. So the A and E is letting you know what kind of structure that you're looking at. Gasoline is octane. So that's letting you know that there aren't any double or triple bonds in that it's all single bonds. There's a chemical, or there's a formula that you can use for it. It's whatever your number of carbons is. And then my hydrogen number is that number times 2 plus 2. And so why is it 2 + 2? Well, let's go with a super simple one of C3H8. So this was the homework one. I've got 3 carbons all connected up to each other. So each one of these has 2 hydrogens on them. So that's why it's the number of carbons times 2. And then what I need is 4 bonds for every carbon. So then I have to tack an H onto the ends. And that's why it's also +2. So every carbon has 2 H's, and then the end carbons have a third H each to basically plug the ends up, make sure everybody's happy. Unless I'm a ring structure, then I don't have to add those because those carbons would come around back and attach onto themselves. You can do that with propane. It's not super stable, but you can force it. All right, so we're going to talk about the nomenclature. IUPAC, that IUPAC is the governing body that pick the names for all the elements on the table, and picks and approves the names given to different things. And then there's a nomenclature structure for naming things. So let me pull up. So if I'm talking about glucose, specifically D-glucose, which you haven't talked about what the D means for glucose. That's his name, glucose. This is an IUPAC name. So we heavily use molecules. Instead of using their IUPAC name, we will give it a name like Bob. So we won't, but when we're finished with this, we'll come back to this and break this apart and understand what's going on with this. The IUPAC naming is very German in its construction. Do you guys know how Germans named planes? Like the word for plane in German. They took the word for air, they took the word for bus, and they literally just glued them together. So it's an Airbus. That's what the plane is. So when you're looking through this, what you've done is you've busted apart every single piece and put them together in a systematic way that is easy once you understand what the system is to follow. So what you're going to find out, so what is that part right there? HEX. 6. So I'm talking about a 6 carbon structure. So right off the bat, this huge complicated thing, I've only got 6 carbons here. What's the AN mean? We're talking about it right now. Okay. We're talking about alkane nomenclature. Where is it? These guys. So it ends with an AN. And then what we're going to find out is anything that ends in an OL is an alcohol. So this is telling you that it's a 6-membered, 6 carbons, no double or triple bonds. There's alcohols, at least an alcohol, and the rest of this we'll talk about a little bit later. This is a little more complicated, but what this is telling you is 1, 2, 3, 4, 5. These are positions on the carbon, on the structure, saying that there are 5 hydroxyl groups, 5 alcohols. attached on carbon number 2, 3, 4, 5, and 6. Then again, we'll talk about this thing a little bit later, but this is very, they're looking at it and then they're telling you what each piece is. And they put the whole word together in a systematic way. But if somebody would, if I would have started off our conversation talking about glucose on day 1, talking about 2R, 3S, 4R, 5R, 3, 4, 5, 6, pentahydroxyl hexanol, you would not be interested in having a longer conversation about that.
Sorry.
What'd you do for Memorial, anything?
Had no service over the weekend. I was gonna download a documentary and watch it, but that's it.
So what I'm getting at is, when you look at a name like glucose or a name like water, those are just names that we use for everyday purposes when we know that they have a particular IUPAC chemical name. So everything has got one of these IUPAC names. If I, let's do, let's see. This is one of the most sold drugs right now. It's for cholesterol, and this is Lipitor. So these names keep getting longer and longer, right? What about sorry, trying to find what did I pick the other day? You get the point. That these, how about if I do? So, when we're going to be naming these things, we have to keep in mind that any of these names could have these 3 pieces. It might have a prefix, it will definitely have a root, and it will definitely have a suffix. So for the root, that's literally just telling you how many carbons are in the structure, in the main structure. And the prefix is telling you if there are anything attached to that main structure. And then the suffix is telling you what kind of thing you're looking at. Am I looking at an alkane, alkene, alkyne, ether, ester, amine, amide, any of those organic or any of those functional groups that we talked about a little bit earlier? I would name my molecule as a whole based off of what that thing is, the most important thing. So we need to remember that we've got these 10, we'll just go up to 10. We won't bother going any farther than that. That each of these prefixes are what we're going to be using for our root. So meth would be just 1 carbon in the structure. So methane, methanol, those are the 2 most common. We talked about oct being octane. And so I mean, meth, eth, propane, bute, those are the weird ones. And then 5 through 10, we've seen those prefix numbers or names before. So we'll go through these rules real quick and then we'll do examples and we'll use the rules so they make a little bit more sense. So you need to find the longest continuous carbon chain, and that will be the root. And then you're going to number the chain nearest to the first substitution on the carbon. If there's a side chain or an alcohol group attached, whichever end it's closest to, that carbon will be carbon number 1, regardless of how it's drawn. You'll give the location of that substitution on that main body. You're going to put the constituent side chains or functional groups in an alphabetical order, meaning meth, F comes before meth. And then the syntax is commas between numbers and dashes between numbers and words. So the complicated way to talk about this. So the first one, this is the correct name, and the second one is the incorrect name. So what you get when you put this drawing up, so usually if this drawing goes up, so a person will want to go 1, 2, 3, 4, 5, 6, 7. So this is a 7 carbon chain, and they're calling this the main chain. So what's wrong with that? The other way is longer. 6, 7, 8. So that's my chain, making this part the side chain. So here is the side chain on my main chain. So just because the thing turns, don't get sidetracked into thinking that's the correct way. Okay, so why is this? So let's talk about the correct one. 4-ethyl octane. So let's start with the root. It's oct. It's oct obviously because there's 8 carbons there. Why is it octane? Why is it ANE? It's all single bonds. Okay. So now this part right here takes care of all of this part of the molecule. Everything that I have highlighted red, that has already been named with the word octane. Now what I need to do is manage this piece here. And so the first thing I want you to recognize is there's 2 carbons there. If it's drawn out in a structural format, it's really easy to see, but I don't want you to get hung up thinking 1, 2, 3. This is not 1, 2, 3. It's just 1 and 2, because this one here is already part of the main chain. So it's things coming off of the main chain that we're counting. So there are only 2 carbons in this side chain. So if there's only 2 carbons in the side chain, 2's prefix is what? What was 1? Meth, eth, propane. So this is a 2 carbon side chain. So then the word that you're going to use is F. That's the prefix that you need. And for alkyl groups that are side chains, you say whatever the prefix is followed by YL. So in this case, it would be ethyl. Now I have to say where that side chain is attached to the main chain. So in this case, 1, 2, 3, 4 gets me to the chain sooner than 1, 2, 3, 4, 5. Okay with that? So you would start at this end to get to the side chain. So that's where the 4 comes from. So that's 4, and then F is the fact that it's 2. YL is the side chain. So I don't need any punctuation between the Y, L, and the OC. They're just letters, so you can just run them together. Although sometimes people put a space in there for clarity's sake, especially if it's longer. But I do need a dash between the 4 and the E. So when I look at that name of that molecule, I think, okay, so there's a side chain on carbon number 4 that this whole chain is 8 long, and there are only single bonds in this chain. think what you're gonna find is going from the structure to the name is more difficult than going from the name to the structure. So if I'm looking at this. Going from this name here, okay, so I see oct, so I'm like 2, 3, 4, 5, 6, 7, 8. All right, so I got 8 here. It's ain, so all of these single bonds are correct. Then I look, all right, number 4, 1, 2, 3, there's number 4. What do I have on number 4? I've got a 2 carbon side chain, so 1, 2. So it should be fairly simple to go from the name to the formula. It's just usually a little more confusing to go from the formula, so from the structure to its name. Now, I want to be clear about these two. Although the one on the right is technically wrong, it's not terrible. It's not fundamentally incorrect. Why? Let's take this name and draw the structure. So 8, 2, 3, 4, 5, 6, 7, 8. All single bonds, so I'm good at that. Then I go to carbon number 5, 1, 2, 3, 4, 5, and I draw an ethyl group. Okay. So why am I saying that that starting off with the 5 isn't that bad? Before going the other way, I actually have the correct chemical structure. So there's nothing wrong chemically with it. It's just grammatically incorrect. So we've all seen Star Wars. So the second one is like how Yoda talks. He'll say something to be like, okay, I understand you. You shouldn't have said it like that, but I understand what you're saying. So the same situation with this. The second one isn't the norm and isn't how you should write the word down. But it's okay. I'm going to get the correct structure out of that name. And the whole point of writing a name down is so a person can think about the name and then come up with the correct structure. So the second one, although it's grammatically incorrect, it's not structurally incorrect. So it's not a terrible mistake. A terrible mistake would be writing 6 ethyl octane or 3 ethyl octane. That would be a completely different molecule. The connectivity would be incorrect. And so you'd go grab a wrong molecule to run in your experiment. You okay with that? All right, so let's talk about this. The first one's correct, and then the next 2 are incorrect. So tell me what's wrong with the middle molecule. Its name. This is the numbering. What's wrong with the numbering? They just have it from the wrong side, right? The correct name counts from the left, giving you smaller numbers. The incorrect way to count this is to count from the right-hand side, giving you larger numbers. It's one of those grammatical errors. Right? I'm still going to get the same structure out of it. It's just I should count from the left side because that will give me smaller numbers. What's wrong with the last one? the number isn't the dictating factor. What I have is the alphabeticalness of it. Again, these are both grammatical errors. Both of those names, those incorrect names are going to give you the correct structure. So it's not a terrible thing. We've got some sidechain rules that we want to talk about. So first off, break the name down for me on that very, very first one. Yeah. So tell me something about it based on its name. What else do I know about the main chain? It's all single bonds. Okay. And then, so I've got this octane, this 8-chain single bond chain. And then since there's a number there, that's letting you know that there's a side chain. And in this case, tell me about the side chain. It's a probe. And so that means that its side chain is only 3 carbons long. Why do I have to have 2 different names for this 3-carbon side chain? Those are 2 different molecules, 2 different melting points, boiling points, vapor pressures, chemical reactivity. So they are different molecules. Not a ton different, but they're definitely different. So I need different names for that. Does it make sense that I need the different names? So this, for the first one, the side chain is where we might expect it to be connected. It's connected to the first carbon in the chain. So then I've got a sequence of 3 carbons. The second one, it's still 3 carbons. So the side chain is still a propyl, but this one's side chain is affixed to the middle carbon instead of the end carbon. So I have to give it a different name because it's a different substance. And so iso means different. It doesn't mean middle, it means different. So if the normal version has the side chain, the 3-carbon side chain, the propyl group attached to carbon number 1, sometimes you'll actually see an N, a lowercase n put in front of the 4. It'll be N-4-propyl octane, letting the person know that it's normal version. And actually it's abnormal. If these molecules are allowed to form on their own, the second one is going to be the one that's going to be formed like 90% of the time. ISO version. So what I'm doing here is I'm attaching a propyl side chain to a longer chain, and I need to have 2 different ways to name it because there are 2 different ways it can be attached. What if it connects to carbon number 3? I have an example for carbon number 1 and carbon number 2. What about carbon number 3? Oh, I don't have a third name. Carbon number 1. Okay. So with the propyl groups, you only have 2 options. But what about the butyl side chains? So tell me about the name of this first one in here. Break it down for me. 9 carbons and all single bonds. Okay. So I've got 9-carbon chain. They're all single bonds. And I've got a side chain because there's a number there. And so tell me about the side chain. I got a 4-carbon side chain. Okay. I had to increase the carbon chain to 9 to put the butyl group on, because if I had only 8 carbons, it would be part of the main chain, or could be classified as part of the main chain. Does that make sense? Because if there was only 8 here, then it could be 1, 2, 3, 4, 5, 6, 7, 8 now. Right? This would not be the main chain. So 9 in a row, I can attach 4, and I would have to attach it to the middle carbon. If I attached it to any of these other carbons, then it would be longer that way. Okay, so this one is just 5-butyl nonane, so nonane, butyl, 4 carbons, and then 5 because it's attached to 1, 2, 3, 4, number 5 carbon on this chain. So that would be the normal butyl side chain. But just like with the propyl, there were 2 versions. There was attached to the end or attached to the middle. There are multiple versions. I can attach 4 carbons as a side chain. So the first one, I'm attaching it to carbon number 1, the normal position. What about the next one? Does that name make sense? 5-sec butyl for the side chain. What's that trying to tell you? It's just attached to the second carbon on the 5 carbon side chain. That's it. Nothing else to it. How about the third one? Different. It's kind of attached to the Y shape. Really what it looks like is I've got a 3 carbon side chain, and my 3 carbon side chain has a side chain of 1 carbon. And so because that's the 4 carbon side chain structure, I'm going to call that isobutyl. And then what about the last one? It's tert. The other, you could get rid of the tert part and just write T. It's kind of in the shape of a T. Are we okay with that? So the reason we're calling it T or tert butyl is because, tell me something interesting about that carbon on the side chain. What's peculiar about that 1 carbon on the side chain? It's only connected to other carbons. And so a carbon that's only connected to other carbons is called a tertiary carbon, and it's phenomenally unreactive. It is, to get to that carbon to chemically react with it, you have to knock off the other carbons around it. So it is chemically safe. So if you're trying to build a molecule, so let's say you're trying to build a drug, but you need to protect something, you could build a tertiary carbon structure. So that thing can be protected as long as you need it to be protected. So I have 4 different possibilities for side chains that have 4 carbons. One where it connects to carbon number 1, one where it connects to carbon number 2, one where it connects into Y shape, and one where it connects into a T shape. And those are the only possibilities. And we're not going to move on to the pent. What do you think happens when we go to pent? We get more options because there's more ways to take 5 carbons and then hook them up. We could even hook them up into a ring structure if we wanted to. Doesn't really work for 4 carbons and basically like a square shape. It's not very structurally sound. Like I told you, we could put the 3 carbons in the propane into a ring structure. It doesn't want to do that, and it doesn't last for very long. The same situation with 4. It doesn't want to be in 4. 5, you've spaced them out far enough where it can be structurally sound, and it's ribose. So, or deoxyribose. So obviously nucleic acids for DNA and RNA work with a 5 carbon circle. And also fructose is a 5 carbon circle. So 5 works. The most stable version though is 6. So that's why there's a lot of benzene type molecules around, because 6 is very stable. 7 could be stable. It's just not seen as much. So greater structures, the more, it's kind of harder for the ends to get attached. So 6 is basically the sweet spot. Okay, so let's talk about something called an isomer. I will let you know that we have just been talking about isomers. All of these things are isomers. And so what's an isomer? Isomer is same chemical formula, different structural formula. So for this example, butane. So let's break the word butane down. So what's bute mean? That's 4.
I can't remember this for starting. And then Propane's easy because I have the formula for propane memorized.
All right, there you go. You just memorize that. That's propane. So breaking the name down, 4 carbons all attached to single bonds. So that's what we have, 4 carbons all attached to single bonds. The chemical formula is C4H10, and I know it's C4H10 because there's 4 carbons. Then I double it, plus 2 gives me 10 H's. So each one of these carbons has 2 H's, so that gives me an 8. And then I tack the ends on, and that gives me 10. So it's C4H10. This is also C4H10. But they are not the same molecules. The butane molecule is about 1,000 times more reactive than this propane molecule. Why is this a propane molecule?
Because it uses 3 carbons in
The main chain is only 3 carbons long. It's got a side 4th chain, but it's a 3 carbon chain with a 1 carbon side chain. So this is 2-methyl propane. Are we okay with me saying that the 2 isn't super important? Can't be anyplace else, right? So this has several aliases. Its official IUPAC name is 2-methyl propane. You will also see methyl propane, but you will also see isobutane. So what we're saying is it's a butane molecule, but what's the iso mean? But it's not correct. It's not in its normal way. It's different. So it's butane. So I know that the formula for this has to be C4H10. And so there's only 2 ways to connect up C4H10. Those are the 2 ways. So what are these things? These are isomers of each other. Same chemical formula, different structural form. So we get to, when we're in inorganic chemistry and I give you a formula, you pretty much know what that thing is because the formula stays the same. The issue is when I'm talking about organic chemistry, those C's like to attach to themselves in whatever way they want to attach to themselves. So now all of a sudden the chemical formula is like, unless it's really small, it's not super useful. So C. What is that? Maybe. What else could it be? It could be a heptane. It could be a hexane. It could be a pentane, right? Why? Well, here's my octane, 2, 3, 4, 5, 6, 7, 8. Here's my heptane, 1, 2, 3, 4, 5, 6, 7, and then there you go. That gives me 8. But that was random, right? Where else could this have been put? There, or there. 3 different possibilities for methyl heptane. So what's the name of this one? We already said it's hep for 7. It's ane for single bonds. What's the side chain? 3? No. How long is the side chain?
Mod is it?
How many carbons long is the side chain? 1. So it's a meth. Where is it? Doesn't matter which direction I count from, it's 4, correct? So it's 4 methyl heptane. What else could it have been? 3 methyl heptane. Could be 2 methyl heptane. And that's it for names. Because if I put it here, that's 3. If I put it here, that's 2. And if I put it here, then it's octane. Okay with that? So there's a heptane. So what do we got here? I got a hexane. Now I've got 8 total carbons. I have that chemical formula. So I'll write down hexane. It's hex because it's 6, it's ene because it's single bonds, and then tell me the rest of it.
3 methyl, 4 methyl.
That's it.
Okay.
Except we're gonna sandwich those together. And so we're gonna say 3, comma, 4, and then we're gonna put a dash here, and then I'm gonna say di. It's dumb and redundant, but it is what it is. We're okay with that? So what else could it have been? It could have been F, right? It could have been that. Could have been 3-ethyl hexane. It also could have been. Okay with that? Could have been 2,3 dimethyl hexane. It could have been 2,5 dimethyl hexane, right? So how helpful is this formula up here? I know I got 8 carbons, that's what I know. I know I've got 18 H's, so I know it's all single bonds. So great. But if you guys pulled out 8 carbons and 18 hydrogens and started slamming them together in any way that they would fit, you'd end up with several isomers. Lots of isomers, actually. Okay with that? This is octane, but this isn't what we buy. What we buy at the gas station is that. Take the octane and we crack it and we turn it into this other molecule. So name that guy. Longest chain.
5.
Okay, so what's 5?
And
How do I end it?
8.
It's all single bond, so it's pentane. So I got a pentane molecule. So I have named these carbons and hydrogens so far. Those are taken care of. So what do I need to name now?
Other gas. Why
So-
does everyone have 2 coming up?
Because it can.
This is how it is. Just decided that's what I wanted. Propyl.
It's not propyl because they're not connected to each other. So what are they? How long are each of these individual side chains?
All 1.
They're all one, right? So, all right, now. How many of them are there?
3.
3, so it's tri methyl. Where are they? Give me, that's only 2.
2, 2, 3. No way.
2,2,3 trimethyl pentane. When you go to the gas station and you buy 92 over 87 or 89, you get more of that. If you buy like a STP gas treatment, it's 100% this stuff. And so it makes your car burn hotter, faster, better fuel efficiency, but obviously it's more expensive. It's like buying bad. Have you ever had like super expensive olive oil? My wife bought some. It was a small bottle. It was about this big, maybe 12 ounces total. I am utterly not joking when I say that I would have no problems tipping that thing up and drinking it right out of the bottle. It was that tasty. It was like eating olives, except there wasn't anything to chew. Like that's how good it tasted. I wouldn't do that with regular olive oil. I'll cook with it, but I'm not gonna just drink the bottle. So Same situation here. Your car getting straight 2,2,3 trimethylpentane is like you drinking the best of whatever you could possibly buy. So again, that C8H18, not super useful. Because again, we could have put those methyl groups in several different places, right? It could have been 2,3,3, or it could be 2,3,4. So we've got multiple isomers to go along with whatever our chemical formula is. So this is why organic chemistry can be fun, but also can be kind of a pain in the butt because you can pull it apart and put it back together in a different way. And nature's had billions of years on this planet to do this. And so it has made lots and lots of stuff. Well, you think about the complex nature of DNA, or you think about the complex nature of proteins, of what was sucrase? Do you remember that?
Source,
No, you're forgetting something.
ace,
You're forgetting the ACE.
it's single bond.
Nope, not single bonds. Totally different thing.
Here's sucrase.
No, it's in your mouth.
It's not referring to a functional group, is it? No.
It is not referring to a functional group. There's your sucrase. It's the enzyme that disassembles sucrose. ASE is telling you that it's an enzyme. So sucrase works on sucrose to disassemble sucrose into glucose and fructose.
The bottom one looks nice, bottom right.
The bottom right looks nice. The rest of it is like, what the hell? I mean, there, it would need to be an IUPAC name for this. These alpha helical structures are amino acids. So the reason that they coil in themselves is they have side functional groups and they're like, oh, look over there. I got this chain, but here and here on the chain are attracted to each other. So they get closer to each other by twisting. And so each one of these little twisty segments are portions of the chain that is very symmetrical. Same situation with these beta pleated sheets. They actually look kind of like staircases. And it's like a couple of amino acids here form some kind of interaction with a couple of amino acids here. And then that same thing forms a staircase. And then we don't want to connect these things. It looks a little chaotic. But what does this thing do? A sucrose molecule lays into it, separates into glucose and fructose, and it goes on its merry way. If you don't have this molecule, table sugar would be, you poop it out. It would be completely useless to you. What do all newborn babies have to have as part of their protein array? What's milk sugar? Lactose. So lactose is a carbohydrate composed of two sugars. You can't consume, lactose doesn't do anything other than transport two sugar molecules. It transports glucose and the galactose. So what's the baby need to do? Its main energy source is lactose. And lactose itself is completely useless as far as energy goes. It's literally just the transport mechanism. So what's the first thing the baby needs to do with the lactose?
break it, it has to use lactase and breaks it into glucose and galactase. That starts in the mouth, also happens in the small intestines, because you've got it in both places, but it breaks apart that sugar into its two components. And then that galactase is a glucose molecule with the alcohol group on the wrong side. And so then you've got another molecule, another protein enzyme called galactase that transports that sugar, that alcohol group to the correct portion of the sugar. So when we were talking about enzymes, we talked about transferases. And transferases were molecules of enzymes that would take a functional group on one part of a molecule and move it to a functional group on another molecule. 100%.
Like the lactase or galactase.
Yep. I know it's in here somewhere. Right, so here's the lactose molecule itself. So here's a glucose and a galactose. Do you see what's wrong with it? Actually, let me put them up here. This is the sugar that we use for everything. What's wrong with this sugar molecule? Got two problems, right? The biggest issue is this OH group over here is up. Where on the glucose, the OH group is down. Okay, so initially what needs to happen when the lactose is taken into the body. So it's literally transporting these two sugars connected to each other to save space. So these two sugars go into the body. This is the main carbohydrate that's in milk. And so now the first thing the body needs to do is break those two things into their constituent components. The glucose just goes off and does its own thing because it's already in the form of ATP. But this guy's messed up. This OH group needs to be put to the other side. So there is a protein in your body, an enzyme called galactase. And galactase takes this functional group and puts it over here and takes that hydrogen and puts it over there. If that doesn't happen, baby's dead in a week. It's called galactosemia. It's uncommon, but not so uncommon that you can't think about it. So, you know how people of the same cultures like to marry into each other's cultures? Unusual for cross-culture people to get married, just is. You usually hang out with the people that are part of your culture, and so you end up marrying somebody as part of your culture. So there is a segment of a Jewish population, and when I say Jewish, I don't mean the religion, I mean the actual people, the genetic heritage of Jewish people in a section of Eastern Europe that was surrounded by mountains, and it was kind of difficult to get out. So what ended up happening is this smaller Jewish segment sort of kept interbreeding with themselves. It was tens of thousands, hundreds of thousands of people, but if you block that off and it's only this small segment of people, so this genetic defect formed and was perpetuated because they didn't have a way to test for it. And it totally sucks because if both the parents have it, there's a 50% chance that the child will have it. And so that means there's a 50% chance that the kid's going to die at birth. We're talking, this has happened for at least a couple of thousands of years. We can manage it now. There's a really peculiar thing that happens with these babies is if you pull the eyelid down, there will be a red spot on the sclera, the white section of the eye. And then you will know that that baby has galactosemia. And so what can't you do? You can't breastfeed them. You have to give them some kind of formula that has galactose taken out of it. So they would function fine with high fructose corn syrup milk, which is what most baby formula is, high fructose corn syrup, because it's cheaper, plus all the proteins. So now, if you're Jewish and you're going to marry somebody else that's Jewish, and again, not the religion, the subset of genetics that make a person Jewish, you might, like if you're like, maybe we should get married, they'll actually do genetic testing
Like, do we both have the galactosema gene? And if we do, then we probably shouldn't get married. Like, there's no reason to do that. So we've been able to deal with that. It's mostly taken care of itself, but not completely. Some people still want to get married even though they've got it, and then they might have a baby with galactosema. And so this isn't lactose intolerance. Lactose intolerance is I can't separate the molecule. And so that forms gas bubbles in the intestines once it gets down there, and then that's uncomfortable, but not life-threatening. This is completely different. This is galactosema, and it's definitely ridiculously dangerous. But again, we could manage it. Babies form, the doctors know now that if two people of Jewish descent got married, they'll just immediately be like, how's that baby doing? No red dot, good to go. But red dot, then I'm sorry, you can't breastfeed. Gotta give them the special galactose-free formula. And then they kind of sucks for them for the rest of their lives, right? What things do you buy at the grocery store that have milk in it? Everything. That industry has done a good job of inserting itself into everything so they could make as much money as they possibly can. So a person with galactosema has to shop on the exterior of the grocery store. Walk around the outside, stay away from the middle. The middle is where all the processed stuff is. And you will look at something and it'll say whey protein. Well, that came from milk. So the whey protein's gonna have lactose in it, so they can't eat that. I don't know how we got there. Whatever. Different structures for things. Okay, yeah, glucose, yeah. So galactose and galactose, those are isomers of each other. One you need, the other one you need to convert into glucose. Sucrose is also got the same chemical formula. It just needs to be converted. So there's a protein in your body that converts sucrose into glucose, unless you're not doing anything. Do we know this? That if you're not currently exercising and your blood sugar, if you're exercising and your blood sugar is down, your body will take fructose and turn it into glucose and turn it into blood sugar in your liver, and it'll be like an instantaneous kind of thing, and feed that into your bloodstream to replace lost glucose. But if your blood sugar is normal, when the sucrose comes in, it is immediately turned into adipose tissue, fat. So when you're eating table sugar or high fructose corn syrup, which is just table sugar modified with more fructose in it, and you're not actively engaged in some sort of activity, that will immediately be turned into fat. That is what your liver's enzymes, they see it and they're like, store it for winter, store it for winter. So I've seen this probably 3 students. One of them I knew before she came into class. She was always a little chubby, and she decided to just the only thing that she did was stop drinking soda. And by the end of the year, she had lost 50 pounds and was just this tiny little girl. And so 2 other people in my class have done that same thing. They came in and they had over the course of the year lost 50 or more pounds because they stopped eating table sugar and high fructose corn syrup. Because what's your body do with it? I mean, if you're going to be drinking Gatorade during your marathon, that's totally fine. But eating that cookie in the back, not a great idea if we're just sitting here, because it's just going to get turned into fat. So where do you have high fructose corn syrup? What'd you say about milk? It's everywhere. It's in everything. We do a very, very good job of creating a great deal of calories. There is no reason to have any famine on this planet. We produce way more calories than we as a human race could possibly consume, but we just don't do a good job with distribution. But yeah, high fructose corn syrup, just fructose in general. There's a guy named Lipzig. He's a pediatrician at UCLA, USC, in Los Angeles somewhere, and he did a speech that was like when YouTube was first coming out and like became popular. His speech was one of the most watched things, and it's like an hour and a half long. And during that speech, he says that fructose is a poison and we shouldn't be feeding it to our children. That the amount of obese babies in the United States, there aren't obese babies anywhere else on the planet, just here. So you've got like a 25-pound 9-month-old. That's not right. And it's they're obese, literally legally obese, and it's all because of that fructose. And it's just an isomer of the sugar that you need anyway, which is, you know, the weird part about it. Here's hexane. How many different ways could I make hexane? I could make it with a straight chain. I could pluck one of the carbons off on the end and put it on carbon 2. I could pluck one of the carbons off of the end and put it in carbon number 3. So those are 2 pentane isomers. Or I can make a couple of butane isomers where I pluck both ends off and I plug them onto carbon number 2 and carbon number 3 in my 4-carbon chain. Or I could plug them both onto carbon number 2. And so we go from hexane to 2-methylpentane to 3-methylpentane to 2,3-dimethylbutane to 2,2-dimethylbutane. But not 3,3-dimethylbutane. Right, got to count from the short side. So are they important? Yeah, they're completely different structures. In the same exact way that glucose, fructose, and galactose, and maltose for that matter, they're not the same sugars. These are not the same molecules. Same chemical formula doesn't mean that they're the same thing. One could be, you know, a fat. One could be a poison, and the other one not a poison. You know, I'll call it good for now.